4.8 Thermodynamics. Heat. Heat, as a technical term in thermodynamics, refers to energy in transfer between systems by mechanism other than thermodynamic work or transfer of matter. Objects contain internal energy, not heat. Heat is energy on the move due to temperature difference. Work is energy transferred by force when they move. Heat is energy transferred due to temperature difference. Internal energy. Internal energy is the energy contained in an object due to the kinetic energy and potential energy of its molecules. Internal kinetic energy is the energy associated with the random disordered motion of molecules. It is different in scale from the macroscopic ordered kinetic energy associated with the moving objects. It refers to the invisible microscopic energy on the atomic and molecular scale. First law of thermodynamics. First law of thermodynamics can be written down as follows. In this equation, delta Q represent heat energy change. Delta U represent internal energy change. Delta W represent mechanical work done. The sign convention applied to this equation is delta Q in is positive, delta Q out is negative. Delta U increase is positive, delta U decrease is negative. Delta W out is positive, delta W in is negative. Now let's see special instances where the first law of thermodynamics is applicable. Constant pressure processes or isobaric processes. An isobaric process is a thermodynamic process in which the pressure stays constant. The heat transferred to the system does work, but also changes the internal energy of the system as well. The work done in an isobaric process can be written as delta W equals P delta V. This equation can be further modified as follows. In isobaric process, the molar heat capacity of a gas Cp is given as follows. Here, gamma is the molar heat capacity ratio, that is Cp divided by Cv. R is the universal gas constant. Constant volume processes, isochoric process. An isochoric process, also called a constant volume process or an isovolumetric process or an isometric process, is a thermodynamic process during which the volume of the closed system undergoing such a process remain constant. In an isochoric process, delta W equals 0. Therefore, delta Q equals delta U. The molar heat capacity related to isochoric process Cv can be written down as follows. Here also, gamma is molar heat capacity ratio Cp over Cv. R is universal gas constant. Now, as we said earlier, Cp equals gamma R over gamma minus 1. Leads to the results that Cp over Cv equals gamma, Cp minus Cv equals R. The value of gamma depends on the atomicity of the gas. Atomicity is the number of atoms in a single gas molecule. For diatomic gases, gamma equals 7/5 and therefore Cp equals 7 second R and Cv equals 5 second R. For monatomic gases, Cp equals 5 second R and Cv equals 3 second R. Isothermal processes. An isothermal process is a thermodynamic process in which the temperature of a system remains constant. The transfer of heat into or out of the system happens so slowly that thermal equilibrium is maintained. In case of an isothermal process, delta U equals 0, therefore delta Q equals delta W. Adiabatic processes. An adiabatic process occurs without transferring heat or mass between a thermodynamic system and its surroundings. Unlike an isothermal process, an adiabatic process transfers energy to the surroundings only as work. In case of an adiabatic process, delta Q equals 0 and therefore delta W equals minus delta U O minus delta W equals delta U. Compressing a gas. This figure shows a simple arrangement of a bicycle pump with a blocked outlet. A thermocouple inserted through the blocked outlet allows the air temperature inside the pump to be monitored. Now push the piston rapidly and hold it in position. The thermocouple ought to show a temperature rise due to increase of internal energy of the air. The pushes force does work on the air rapidly. So no heat transfer from the air occurs. Hence, the work done increases the internal energy. Return the piston to its initial position and allow the temperature to return to its initial value as well. Then push the piston in very gradually. No temperature rise occurs this time. Why? You still do work on the air as you push the piston in. However, any slight rise of temperature causes heat transfer from the air, so the temperature returns to the initial value. In other words, heat transfer from the air occurs at the same rate as work is done on it. So, no rise of internal energy occurs. When a process is carried out slowly, the system has time to exchange heat with the surrounding, and therefore the temperature remains constant. Temperature changes during an instantaneous process as no heat transfer takes place with the surrounding. Therefore, a slow process is an isothermal process, whereas a rapid process is an adiabatic process. Cyclic processes. In a cyclic process, the system starts and returns to the same thermodynamic state. If we represent the system changes in a PV diagram, if the cycle goes clockwise, the system does work. A cyclic process is the underlying principle for an engine. If the cycle goes counterclockwise in the PV diagram, work is done on the system every cycle. PV diagram of petrol engine, which is called the Otto cycle. is as follows. There are 7 steps in the PV diagram during a 4-stroke cycle of Otto cycle engine or petrol engine. The 1 to 2 process represent the intake, 2 to 4 represent compression stroke, where during 3 to 4 combustion takes place. That is almost at the end of the compression stroke. 4 to 6 process represent the power stroke, during which 4 to 5 is an adiabatic process and 5 to 6 is represent the heat rejection by the engine. 6 to 7 represent the exhaust stroke, where cycle returns to the starting point back. PV diagram for diesel cycle, which is used in diesel engines, is as follows. 1 to 2 process represent the compression stroke. 2 to 3 represent the combustion of the fuel. 3 to 4 represent the power stroke of the engine. 4 to 1 represent the heat rejection of the engine. And that is the end of topic thermodynamics.